On the second quiz from 2008, I asked this question. We found from a computational fluid dynamics calculation that for this little block sitting in a crossflow like this, the pressures on the front, on here, are well approximated by this equation for pressure, 100 minus 20 y squared pascals gauge. So when y is equal to 0, the pressure is a maximum, and it falls off as we go out towards the edge. The pressure is lower towards the edge in both positive y and negative y. So, first question, is there a stagnation point in the flow? If so, where? Indicate on the sketch. Well, the stagnation point is going to show up right in the middle here. The fluid that's coming along the middle here comes to a complete stop right there. And in fact, no fluid really comes right down the middle. All of it comes down either one side and turns off around the corner like that, or down the other side, turns off around the corner like that. But this is a stagnation point, and that's where the stagnation pressure is going to be. So let's just note that that's the stagnation point. What will the pressure force be on the front surface resulting from the flow? Well, the pressure here is highest, it's 100 pascals. The pressure out here is lower by minus 20 y squared pascals. So if we want to get the total pressure force on the front face acting in the x direction, we're going to have to integrate the pressure over the face. So let's assume that it extends 1 meter into the page in this direction. It's 1 meter wide. Then I'll need to get the force in the x direction by integrating over the area pressure times area. And in fact, I could just integrate over half of the area because the other half is going to have exactly the same contribution. The little incremental area will be like this. It'll be 1 meter wide and dy high. So I'll have integral from 0 to, it's 1 meter high, so 0 to 0.5 meters in y. It'll be plus 0.5 and minus 0.5. And if I'm only going to integrate over this half, I'm going to have to multiply by 2. So 2 times the integral from here to here of the pressure times the width, in this case 1 per 1 meter width. Oh, hang on, it told me it's 10 meters wide. Better read the question carefully. 10 meters wide. So pressure times width times dy, that'll give me the force. That'll be equal to 2 integral 0 to 0.5, 100 minus 20 y squared times 10 dy. 100 times 10 is 1,000, integrated with respect to y is 1,000 y, minus, from there, 20 times 10 is 200, integral of y squared will be y cubed over 3, so 200 y cubed over 3. Evaluated at 0 and 0.5. So this is just the integral carried out here in these brackets down here. 2 times 1,000 y, 100 times 10, minus 200 times the integral of y squared, which is y cubed over 3. So when we take the derivative, we'll get 3y squared divided by 3. And plugging in 0.05 there, I get 2 times 1,000 times 0.5 minus 200 times 0.5 cubed over 3. And for 0, both of those make a 0 contribution. And the answer is, from the calculator, 1000 times 0.5 minus 200 times 0.5 cubed divided by 3. I get 491.7. Pascals. Whoops, no, that's not pascals, it's pascals times area. 491.7 newtons. Now let's check that answer to see if it makes sense. The total area is 10 by 1 meter. So that would be a total of 10 square meters. The peak pressure in the middle is 100 newtons per square meter, 100 pascals, and it's lower off to the sides. If it was 100 all the way through, then that would give me 1,000 newtons. But the fact that it's falling off to the edges as y increases, either in the positive or negative direction, means I'll get less than that, and it turns out I get about half as much. So that answer checks out.